Good morning to everyone. I want us to go through section 6 of week 1. That's under test of hypothesis concerning proportions. In this unit, we turn our attention to test of hypothesis that will enable us to decide whether the true value of proportion or population proportion equals a given constant. Now, the sample proportion is given by this formula. That's the formula for finding the sample proportion. Now, when we say proportion, let me just give an example. Now, let's say 10 students from UCC were sampled to share their view. So it means that N is going to be 10. 10 students have been sampled to share their view if UCC should be awarded the best school in Africa. Now, out of this sample, 6 of them said yes, they should, and 4 said no, they shouldn't. Now, if our interest or the success is those who said yes, then it means the 6 is going to be the number of success, and therefore our proportion, which is called p hat, becomes 6 out of the total sample, which is 10. So that is the meaning of p hat. It is the proportion of the success or those that we are interested in. Now let us move on. Under hypothesis of proportion, we are dealing with binomial probabilities. Also, there are 2 cases involved. These ones are expected values and the sample variance. Let's go to the large sample case. Now, whenever you have this type of question, you analyze the question and look at the sample chosen. If the sample is greater than, if S is greater than 30, then we call that sample as a very large sample. And whenever that happens, then we approximate the whole distribution to a normal distribution. So we are going to apply this formula. Whenever you see n into bracket 0, 1, it shouldn't confuse you. It is only telling you that we are dealing with a normal distribution where the 0 stands for the mean of the normal distribution. If you have a normal distribution, the mean is always 0, and the standard deviation is 1. The standard deviation, the distance from where the mean is to the very end, is 1. So it has a standard deviation of 1. That is what we call normal distribution. So this one is only telling you that this formula is for normal distribution. And we apply this formula whenever the sample size is greater than 30, which is a large sample size. Now I want us to pick an example, then we solve. Let's look at this question. A fruit drink manufacturing company has indicated that it will adjust upward the price of one of its cherished drinks by 10%. If proposed tariffs by the government are implemented, suppose that a survey of 1005 customers, so it means that this 1005 becomes our sample size, who currently purchased this brand of drinks, shows that 67 of these customers say they will not purchase. So now we are saying that out of this sample, when they were interviewed, 67 says that they will not purchase if the tariff should go up. So it means that this is our interest, and therefore our proportion is going to be, thus P hat becomes this 67 divided by the total sample size, which is 1005. Then we can just break it down to that to give us somewhere 0.667. That is our proportion. Now once we know our proportion, also the question has given us an indication here. Let's go to the null hypothesis. Our null hypothesis is to test that the proportion is equal to 0.10. Now this proportion here, this one, is called the hypothesized proportion, and it is indicated by P naught, which is 0.10. It's called the hypothesized proportion. So now we know our calculated proportion, and we know the hypothesized proportion. We know our sample size to be 1005. So we are true, and there is a significance level, which is the alpha level, 1%. 1% is the same as 0.01. So with all these parameters, you have to quote the formula nicely. So we have already calculated for the proportion. Then now we are going to use the t-test. No, we are going to use our test statistic, but this time is the normal distribution. That's the z-test. So just substitute the values. Remember the formula is z is equal to p naught. That's the calculated proportion minus p hat minus p naught. The p naught is the hypothesized proportion, all divided by the square root of p naught into bracket 1 minus p naught, then over n. The square root affects everything. So that is the formula here. Then we substitute everything. P naught was p hat, the calculated one was 0.067. Then minus the p naught is 0.10. That is coming from the null hypothesis. Then all over the square root of p naught again, 0.10 into bracket 1 minus p naught again, all over the sample size. And when you calculate this, you will get this. So we are going to get this value. Now, the next thing we need to do is this z value is called the calculated z value. It's called the calculated z value. Remember, we are dealing with a normal distribution. Normal distribution is symmetrical. So my critical values can be here. So I have to look for these critical values 1 and 2. Remember that the alpha size or the significant level given was 0.01. That's my significant level. Let's take note of that. Then also looking at the question, you realize that the alternative hypothesis is P is less than 0.10. So it means we are looking at just one tail. It's a one-tail distribution. So this is the region we are interested in. We are interested in this region, and this region is a rejection region. When we are able to meet this region, then it means we have to reject. We need to reject. But one thing you have to know is that a normal distribution is symmetrical. So if I am working on the left hand side, the area here to the left of this critical point is the same as the area here. So I can also use this region. This region is still a rejection region. So if here is my 0.01, then it means that if I subtract this from 1, let me do that. 1 minus 0.01 will give me 0.99. So it means that instead of using an alpha value of 0.01, I can also use an alpha value of 0.99, because if here is from 0.99 to infinity, the area there is the same as from negative infinity to 0.01, because the normal distribution is symmetrical. So let us go and read this from the Z table. So this is my Z table. We are looking for an alpha value of 0.99. We are looking for an alpha value of 0.99. So what you need to do is to go through all these decimal points and look for a value which is most closer to 0.99. So let's do that. So going through them, I can see 0.2, 0.6, 0.8. So I am seeing 0.9 somewhere here, but 0.91. So let me still go up. Let me go down and see. Okay, so I am seeing, when you look at these values, you have to scroll through all 0.92, 0.96, 0.97, 0.98, 0.99010. So you could see I'm looking for 0.99. This is what I am looking for. When you come to this place, I have 0.99010. Here I have 0.989. I have 0.99036. So you see that you have to ask yourself that among all these values, you will see that 0.99 is somewhere here. But which of these values is the most closest to 0.99? And I can see that it is 0.99010. This one is the most closest to 0.99. So you ask yourself that if you look at the normal distribution, you realize that they have written here Z. So it means that the values on the horizontal and the value on the vertical, when you put them together, will form the z calculated value. So I can see that where I am getting the 0.99010 is 2.3. So let's write that down, 2.3 on the left. Then when we go up, it is 0.03. So you only have to 0.03. So 2.3 plus 0 is still 3, then 3. So it becomes 2.33, and that becomes your z value. So let us go back. We now know that our z calculated value is 2.33. So when I come back here, my z calculated value is 2.33 here. So this 2.33 is the critical point. It's my critical point. Because it is symmetric, it means that here will also be negative 2.33. So these are my critical points. So it means that if I have a value which falls within this region or this region, then I have to reject the null hypothesis. So now let's go back to our calculated z value. The calculated z value is negative 3.4874. Now pick the absolute value of this. The absolute value of this z value becomes 3.4872. And compare it to the calculated one, you will realize that it will fall outside. So it will either be here or here, because any value here will be less than the absolute value of anything here will be less than 2.33. Therefore, if let's say the calculated z value was to be somewhere 2.0 or 2.2 or 1 point something, then you could see that all these values are within this. Therefore, we will fail to reject. But the calculated z value, its absolute value, will fall outside the critical value. It's going to be within the critical value. That is, the critical value is to the left or to the right, and that means that we have to reject the null hypothesis. So that is what they have explained here. If the absolute z value is greater than the calculated one, then we reject the null hypothesis in favor of each one, and then we conclude that the proportion of purchasers who will stop buying the product is less than 0.10. So that is for this one. Now let's move on to the next one, which is small sample case. Now, whenever the sample case for proportion is very small, we can't use the normal distribution. If n is small, the test concerning proportions are based directly on binomial probabilities. Here we don't use any formula. We only go strictly by the binomial probability, which is found in the statistical tables. So let me skip all these things and let's pick an example on that. So let's consider this example, which is example 11. It is claimed that 40% of patients that attend a certain clinic on any day are smokers. 40% of them are smokers. Supposed on a particular day, 3 out of a sample of 13, so take note of this. Our sample size is 13, and you could see that this is less than 30, so indeed it is a small sample. Whenever it is a small sample, you need to use the binomial probability table and not the Z table. Okay, so this 40% is our hypothesized proportion. 40% is the same as 40 over 100, and that will give us 0.40. So our hypothesized proportion for the null hypothesis, we are saying that it should be equal to 0.40. Then the alternative is saying that it shouldn't be equal to. Remember, this one will have two directions. Either P should be less than 0.40 or P should be greater than 0.40. So two directions. So it means that this is a two-tailed hypothesis. So we need to take note of that. We have been given a significance level of 5%, and we know that 5% is 0.05, but because it is a two-tailed hypothesis, we divide it by 2 to get 0.025, and we are going to call that as K. So our K is 0.025. So now we know X is equal to 3. This was the interest. Those 3 out of the sample attending the clinic were found to be smokers. So we are interested in those who are smoking. So this is the sample of interest. So if we were to be using the normal distribution, then our P naught is going to be 3 over 13. But this case, because the sample size is small, we will not use this, and we will not use the formula. We are going to use the binomial probability distribution. So let us look at that. Let's look at that. So that is the question. It's the same question here, and we are to. So we have our hypothesized proportion 0.40. The alternative is here, which is a two-tailed hypothesis. We have been given the success, that is those who smoke, to be X is equal to 3, and the sample size, which is very small, less than 30, is N is equal to 13. So this is where I want to explain. I want to explain this whole thing for you to understand. This is coming from the binomial table, the binomial probability table, with the binomial distribution table with the size N is equal to 13. So when you go to the binomial table, this is the binomial distribution table, you will have N is equal to 13. When you scroll down, you see N is equal to 12. It starts from N is equal to 1, N is equal to 2, and so on. N can take any value. So you have to be scrolling to get to where, let me check if I have it here. The binomial distribution table. Yes, I have it here. This is the table. So you could see that I have N is 13, N is 14, N is 15, N is 16, and so on. So you have to scroll to where you are looking for. So we are interested in N is equal to 13 because our sample size is 13. So you scroll to this point n is equal to 13. It continues. The n is equal to 13 starts from here. So n is equal to 13. We have it here. So that is where we are going to pick our values. So let's go back. So with the n is equal to 13, you could see that the first x value is 0, 1, 2, 3. It goes on and on up to 13. So where n is equal to 13, the x values also ranges from 0 to 13. When you see x is equal to 14, n is equal to 14, x will range from 0 to 14. So always x is ranging from 0 to the n value. Let's take note of that. So that is for the n. That is for the n. Then let's go to our hypothesized proportion. Our hypothesized proportion is the 0.40. So you have to also come here and look for that. 0.40 is here. So we are going to work within this column. We are going to work within this column. Let's take note of that. We are working within this column. Here, 13, they didn't bring anything. What is supposed to be here is 0. Because in the binomial probability, when it is 13, it is 0. Let's take note of that. That's why there was nothing there. Okay. So let us look at it. What we are going to do is look at this rule. Our null hypothesis is p should be equal to 0.40 and the alternative is p shouldn't be equal to 0.40. What was the alpha level? Our alpha level was a is equal to, or in the binomial proportion, a was 0.04, but when we divide it by 2, we are going to get k 0. So we are finding k 0. So it means that because it's a two-tailed, alpha will be divided by 2. Yes. So alpha is equal to 0.25 for two-tailed. Therefore, k, we are looking for k 0.025. Then our k is going to be 0.025. So now what you need to do is come to the table. Start from the top. We are starting from the top. And look at these values. You can see that we have 0.0013 here. 0.0013. We have 0.0013 here. 0.0013. We have 0.00113. Now when we get to this point, the next point here, we are getting 0.0453. This 0.0453 is greater than the alpha value, because our alpha value is supposed to be 0.25. 0.0, sorry, it's supposed to be 0.025. So we are supposed to read from the top till where we see a value greater than this. A value greater than this. So you can see that this value is accepted. This is accepted. But when we get to this point, it is greater than 0.025. So this one is not accepted. Then it means that this has become our critical value, or this is the point that we need to stop. Then let us also read from the down. We are going to read from the down. When we read from the down, we can find, because it is a two-tail test, that is why we are reading from the top and we are also reading from the down. When we read from the down, we can see 0.001, which is less than this, so we will take it. We can also see this one, it is still less than the value, we will take it. Then we will also see this one, which is still less than 0.025, so all these are accepted. When we come to 0.024, 0.024 is also, let me check it well, 0.24, okay, so 0.0243 is also below. Okay, so let us start with the reading again. Let's take note that our critical value is this 0.025. That's the alpha value, sorry. That's the alpha value. So what you do is that come to this column. Let's keep adding from the top. We are going to add from the top. So we are going to add 0.0010. We are adding 0.0010. Sorry, I'm coming. So let me use the calculator here. We are adding from the top. So let's begin to add from the top. So let's add this. Then we add this. We keep adding. So we will be adding till we will get to a value which is very close to 0.025. So that if we should add another value to it, it will go beyond that. At that point, we have to stop. So I can add, so that is what they did here. You add this, then you also add this. That is the value 0.0013 plus 0.0113. That is what we have here. When you add these two values, you will get 0.0026, and you can see that this value is less than this. Now if I want to continue, if I add this value to it, it will be greater than that, and therefore I don't have to do that. It means that this value becomes the boundary point. We don't add, so we are only interested in the first two. And you can see that in the first two, x is 0 and x is 1. So that is how come we are adding from 0 to 1. We are adding from 0 to 1, and those values are this and this. So we only add this and this. We are adding from 0 to 1 with an n value of 13 and with a hypothetical value of 0.04. And if you read from the table, it is going to be this and this. So that is what we have here. Now when you finish, we have to also read from the down. We are reading from the down because it is a two-way or a two-tail hypothesis. So the same thing we did here, we will do the same thing here. So here too, we will keep adding till you will get to where the value is just less than 0.025. So we can add this, add this, add this. When we add this value to it, it will go beyond that. Therefore, we are not supposed to add this. So this also becomes the boundary point. We can't add this one. It's a boundary point because if I should add all this four, it will be more than this. But we want a value just less than this value. So it will be only these three values. So they did that one here. It means they started adding from n is equal to 10 up to n is equal to 13. Remember, here is 0, so they didn't bring anything there. So if you add everything here, you will get 0.0078, and this value is also less than this. So it means that when you get to this point, remember our interest was x is equal to 3. So you ask yourself, where is x? Let's look at where x is. Remember that these are the critical points. 0, 1 is the critical point. Then from 10 up to 13 is also another critical point. So these are the rejection region. This and this is the rejection region. So if this 3 falls, if 3 was to be somewhere here or here, then we have to reject. But you can see that 3 is in between, so 3 is not in the critical regions. These are the critical regions. These are the critical regions. But you could see that 3, x is equal to 3, is not in the critical region, so we fail to reject. So that is it. You can see that since s is equal to 3 is neither less than or equal to 1 nor greater than or equal to 10. You could see 3. You could see that it is from the 10. If any number is greater than 10, it is in the rejection region, or if it is less than or equal to 1, it is also in the rejection region. But because 3 is neither less than or equal to 1 or greater than or equal to 10, then it means that it is not in the rejection region. Therefore, we fail to reject and conclude that 40% of patients that attend the clinic are smokers. Thank you.